Welcome to this explainer. Today, we're jumping right into the fascinating and honestly, kind of terrifying mechanical realities hidden inside an appliance millions of us rely on every single day. The air conditioner. You know, you hit the power button, the cool air flows out, and we rarely give it a second thought, right? But behind that quiet hum is a highly pressurized, extreme temperature environment. And when the mechanics of that environment fail, well, the results can be absolutely catastrophic. So let's crack open the casing on this everyday machine and uncover the anatomy of a disaster. We're going to find out exactly why AC compressors explode.
To really grasp the stakes here, we need to anchor this explainer in a recent real-world event. Take the frightening incident that happened recently in Noida. An air conditioning unit's compressor didn't just casually stop working, it violently blasted apart, sparking a massive fire that spread incredibly fast. And it's super important to note, this wasn't just some electrical short circuit. This was a fundamental, physical-mechanical failure that caused an explosion. It's a pretty stark reminder that we literally share our living spaces with pressurized industrial machines. Understanding how they fail is absolutely crucial for our own safety.
So what's actually pumping through the veins of that machine? Well, it's the lifeblood of your air conditioner, the refrigerant. In these modern units, we're talking about a specific chemical called R32 gas. This stuff is housed safely inside the system, and it's purpose-built for one incredibly grueling task. It is designed to be heavily compressed. The whole magic of air conditioning relies on taking this R32 gas and just aggressively forcing it into a much smaller space, manipulating its physical state to pull heat out of your room. But before we can understand the explosion, we've got to understand the intended design and how this builds a continuous, safe loop when the machine is working perfectly.
Which brings us to Section 1, the normal refrigerant cycle.
Okay, so it all starts in the literal heart of the machine, the compressor. The compressor's entire job is to take that R32 gas and squeeze it. And I mean really squeeze it. It drives the pressure of this gas up to an intense 120 psi, or pounds per square inch. To put that into perspective, a standard car tire sits at about 32 psi. So your AC compressor is forcefully packing this gas in at nearly 4 times the pressure of a car tire. That takes immense mechanical force. And well, basic physics tells us that when you heavily compress a gas like that, you generate heat. A lot of heat. This extreme compression naturally drives the temperature of the R32 gas up to a scorching 80 degrees Celsius. So now, as it's leaving the compressor, you've got this highly volatile, highly pressurized, incredibly hot gas. But it's totally safe as long as it follows the intended path.
Let's just quickly trace that safe 4-step journey. We just saw step 1, the compressor pressurizing the gas. From there, that 80-degree hot gas travels to step 2, the condenser, where it cools down just enough to actually condense into a liquid. Next, it hits the expansion valve, dropping the temperature super fast and trying to turn it back into a supercooled gas. Finally, this freezing mixture enters the evaporator coil right inside your room, absorbing the room's heat to fully vaporize. That's what gives you that nice cold air. Then, it cycles right back to the compressor as a pure gas to start the whole shebang all over again. But what happens when this perfect loop breaks?
Let's look at Section 2, the expansion valve failure.
Right here is exactly where things go sideways. Sometimes the expansion valve fails to convert that liquid 100% back into a gas. Remember, the system is explicitly designed to take the liquid from the condenser, pass it through the expansion valve, and completely transition it back to a gaseous state so it can absorb heat. But, machines aren't perfect. If this valve malfunctions, or if the system gets compromised somehow, it makes a critical error. It leaves unconverted semi-liquid refrigerant sitting right there in the lines.
And this creates a serious rogue element in the system. That semi-liquid mixture escapes the faulty expansion valve and travels into your room's evaporator coil. The coil tries its absolute best to use ambient room heat to boil off that remaining liquid and vaporize it. But because the mixture was wrong from the start, it just struggles, and it fails. Ultimately, that liquid escapes the evaporator coil entirely. It has completely bypassed the system's final safety net, which sets up a pretty terrifying mechanical reality. That rogue liquid is now traveling down the return line, heading straight back to the heart of the system. So pause and think about this for a second. What actually happens when liquid returns to the compressor?
It all boils down to a core rule of physics, a rule that literally dictates the survival or the sudden destruction of the machine. The compressor is a highly engineered pump designed for one thing and one thing only: gas. Gas has a molecular structure with plenty of empty space, making it completely compressible and perfectly safe for the machine to squeeze. But liquid, it is a fundamental law of physics that a liquid is incompressible. You literally cannot squeeze a liquid into a smaller volume. It is physically impossible.
Which brings us to the final breakdown, Section 3, Anatomy of the blast.
Picture this. The liquid refrigerant enters the compressor chamber. The heavy metal pistons of the compressor slam down, expecting to meet the soft, springy resistance of R32 gas. Instead, they hit a solid wall of incompressible liquid. The motor doesn't know it's supposed to stop. It just keeps pushing, generating that insane 120 psi of force. The resulting mechanical resistance is so violent, so unbelievably sudden and extreme that the metal casing of the compressor simply gives way. It blasts itself apart from the inside out, instantly releasing all those pressurized, volatile chemicals. And that is exactly what leads to the massive fires like the one we saw in the Noida incident.
It's a chilling chain reaction, isn't it? And it all stems from a simple, tiny failure in phase conversion. Which leaves us with one very critical question to think about. Is your AC mechanically sound enough to prevent liquid from returning to the compressor? It's not just about getting cold air on a hot day. It's about making sure the delicate physics happening inside that metal box remain perfectly balanced. I really hope this explainer has given you a newfound respect for the invisible, powerful mechanics running right on the other side of your wall. Stay curious, and definitely stay safe.